All right, let's see how we work this problem here. We're looking for the value of an equilibrium constant K for a reaction, an oxidation reaction, where we've got iron metal getting turned into iron 3+. So we've got a single reaction here. We need to find the E0 cell for this reaction before we can look at calculating the equilibrium constant. So let's break it into its half reactions. And so we're going to have two FEs going to 2 Fe3+, and that's going to be plus 6 electrons in order to balance out those charges. And then we've got our 6H+, and we've got to have the 6 electrons there to balance out the charges going to 3H2. So there's our two half reactions. We've got our electrons in there to balance everything out. We've got a set of electrons on the product side, a set of electrons on the reactant side, so we're good to go. We can look up the E0 cells, and so for this first one, the reduction potential for iron turning to iron 3+ is a negative 0.036 volts. Even though this is written as an oxidation reaction, we still use the reduction potential. That's because that's what we look up. We can go ahead and write that this is the oxidation reaction because we see that the iron is losing oxidation. I can spell today. Iron is losing electrons there, and we see that the H+ is gaining electrons, and so that is our reduction half reaction there. If we want to calculate the E0 cell, so E0 cell is going to be equal to E cathode minus E anode is one of the equations. It's the one I generally use. Oh, it helps if I put in this E0. Since it's H+ and H2, that's equal to 0.0 volts. That's our standard voltage there for hydrogen there. So we know that reduction occurs at the cathode, and so I'm going to have for my E0 cell, that's going to be 0.00 minus a negative 0.036. All that's in volts, and so that comes out to be a positive 0.036 volts. So not exactly something you're going to power your laptop with, but it is a positive voltage, and that does indicate to us that it is a spontaneous reaction. But we're not worried about the spontaneity here. We're trying to calculate the equilibrium constant. And so we have an equation that does relate equilibrium constant to voltage, and that is E0 cell is equal to 0.0257 volts over N times the natural log of K. Now we can use that 0.0257 volts since we are at 25 degrees Celsius, and we'll assume that everything else is standard conditions. When we look at the reaction, we see that we needed 6 electrons in our half reactions in order to balance out the redox reaction. So we know that our N value is equal to 6. And we know our E0 cell because we just calculated it. So let's go ahead and plug in the values that we know. And so we have a 0.036 volts is equal to 0.0257 volts over 6 natural log of K. We can move the 6 and the 0.0257 volts over mathematically, and that gives us 8.404 is equal to the natural log of K. And then in order to get rid of that K, we need to raise both sides with E. And so that gets rid of our natural log there. So we have E to the 8.404 is equal to K. And so we get that K is equal to 4.47 times 10 to the third. So even with such a small E0 cell at 0.036 volts, we still get a very sizable K that's in the large size that tells us that this reaction will be shifted far towards the reactant side at equilibrium. So hopefully all of that calculation makes sense. If it does not, make sure that you contact me.